Welcome you all to Principles of Organic Synthesis. At present we study organophosphorus, sulfur, silicon, boron and tin reagents. So far we had one lecture in this topic in which we studied the application of organophosphorus compounds. In particular, we have seen in detail the preparation of phosphorus ylides and their application for the olefin formation. Then also we have seen some related reactions. In this lecture we will study the organosulfur and silicon reagents. In this slide you can see the importance of sulfur compounds. As you can see here, and for example this molecule has sulfone as a functional group which we use as a drug for the leprosy, and this name of the compound is tapsone. And similarly this compound all of you know very well, penicillin, and here you have the sulfur group, and this when you have the thioether, this bicyclic lactam which has the sulfur atom which we use antibiotic, all of you know very well. And now let us look at this compound, the piroxicam. This is a anti-inflammatory drug which is used to relieve the pain as well as swelling in arthritis. So this compound you can see here, this also has a thiol substituent, and this is glutathione is a scavenger for toxic oxidant. Similarly, there are so many sulfur containing compounds. You have here thiol functional group, here thioether functional group, here you have the sulfone, and here also sulfone. And this compound you can see similar, there are several compounds which have the sulfur based functional group, find broad utilities in agriculture as well as medicinal sciences. This compound all of you know very well, methionine is an amino acid. This also has you can see here a thioether substituent, and similarly this artificial sugar, you know, saccharin, this one also has sulfone substituent. So therefore much attention is focused on the development of new synthetic routes for the construction of sulfur based compounds. In this lecture particularly we will focus on the use of organosulfur reagents for the synthesis of olefins and related compounds. Now let us look at here. If you try to remember the earlier class where we studied the phosphorus ylide, if we have the, for example, triphenylphosphine, you can try to react with for example alkyl halide, and you can make phosphonium salt, which when you react with base like sodium hydride, and you can make the ylide. This ylide can be stabilized as we have seen by the d orbital of the phosphorus. Similarly, in the case of sulfur also you can try to make sulfur ylides, and sulfur also has 3d orbital which can make bond with this carbon ion that you generate in the ylide. For example, if you have the sulfonium ion, we have the dimethyl sulfide, you can try to react with methyl iodide, you make the salt, so when you react with base as just we have seen, and you will be able to form the ylide. So this ylide also can be stabilized by the d orbital from the sulfur, then you will be able to form halide. In addition to that, if you compare the phosphorus halides and sulfur halides, this also can undergo addition reaction with the carbonyl compound, as we have seen in the case of phosphorus halides. We have the aldehyde or ketone. For example, you have the ketone which can undergo addition reaction, and you will be able to form betaine, which can convert into the oxaphosphetane, this can convert into olefin. We have seen, and similarly this also can undergo addition reaction. However, you will end up with a different product, we will see in detail later. And if you look at the case of phosphorus, it can have phosphorus 3 can be easily converted into phosphorus 5. Similarly, here sulfur 2 you can have it, this also can be converted into sulfur 4 and sulfur 6. And in this lecture we are also going to study about silicon reagent, but it can exist only in with valency 4, and but sulfur can go 2, 4 and 6. We will study all these properties in their applications. Now let us look at here the preparation of the sulfur halide shown here. As shown, if you have the dimethyl sulfoxide, you can try to react with the sodium hydride, you make this base which can be stabilized by the oxygen, as you can see here. Once we have this one which can now deprotonate from the sulfonium ion, and deprotonation can lead to the formation of this halide, and this halide, as just we have seen, can be stabilized by the d orbital of the sulfur, as you can show here. And similarly, you can also if you have the sulfoxonium ion, you can also deprotonate and similar way, then you will be able to make this halide. This halide also can be stabilized as shown here by the d orbital of the sulfur. You can make these halides. Now, if you compare the reactivity of these halides, they can be readily reacted with the aldehyde and ketones. Even sterically hindered ketone can be readily reacted with the sulfur halides. And here, and in addition to that, if you see the Wittig reaction that undergoes addition reaction with aldehyde and ketone, whereas here this halide can undergo reaction with enone, where it can react with the double bond. You can make the cyclopropane derivatives. We will study later. In addition to that, in the case of phosphorus halide, you get alkene as a product. And what you form this intermediate. Once you form the intermediate, it is converted into phosphine, triphenyl phosphine oxide in this case, and you get the alkene as the compound. Whereas if you, in the case of sulfur halides, you get epoxide as a product. Now, for example, and this your carbonyl compound, it can undergo nucleophilic addition. This as shown here, then you will have this intermediate. Once if you have this one, and in this case, and this one undergoes SN2 substitution here. So, it acts as a good leaving group. You make epoxide as a product. Whereas in the case of phosphorus halide, it makes it reacts with the phosphorus, and which convert into phosphine oxide and olefin as a product. Although sulfur also can make bond with oxygen, but phosphorus make bond with oxygen more stronger comparing to sulfur. Here, for example, in this case, it prefers the SN2 substitution, then it acts as a leaving group, and you will be able to form the epoxide, which is very important in synthetic chemistry, which has been well explored. Stereospecific reactions also has been considerably explored. Now, let us look at only the basic aspects of this reaction, this lecture. Now, let us look at, if you take this cyclohexanone as the substrate, you can try to react with this ylide. For example, if you use this ylide and it can undergo addition reaction as just we have seen, you will have this intermediate. Once you have this one, by it can undergo SN2 reaction and you will be able to get this epoxide as a product, where you generate the dimethyl sulfoxide as a byproduct. So, this one of the efficient synthetic route. If you want to convert aldehyde and ketone into epoxide, you can use the sulfur based ylide, and which can undergo addition followed by substitution reaction, intramolecular SN2 nucleophilic substitution reaction to give epoxide as the product. This epoxide can be further reacted with Lewis acid shown here, and it can be converted into aldehyde. For example, if you have the cyclohexanone, if you want to convert into this aldehyde, see one of the effective synthetic route, you can make the sulfur ylide, which can undergo addition reaction with this ketone to give the addition product, which can convert into epoxide. Once you form the epoxide, you can try to react with the Lewis acid, it can be converted into aldehyde. So, which can convert into in this way you will be able to form the aldehyde as the product. Now, let us look at another very interesting transformation. Now, let us take this dihalo compound. When you take treat this compound with this diphenyl sulfide in the presence of AgPF4, you will be able to get this salt. Once you form this salt now when you react with the base, it can deprotonate, then you will be able to form this ylide, which can undergo nucleophilic substitution as shown here, and you will be able to get this cyclopropyl derivative. Once if you have this one, now you can further react with the base, it can deprotonate, you will be able to form this ylide. Once you form this ylide, as just we have seen, this also you can try to react with aldehyde or ketone. For example, let us take benzophenone, it can undergo addition reaction, you will be able to have this intermediate. Once if you have this intermediate, which can undergo cyclization as shown here, and it can come out by a SN2 pathway, then you will be able to make this compound. Once you form this one, which when you treat with acid, it can protonate. Let us take the simple one. Let us take acetone, and you can form once you form this intermediate, which can open up and you will be able to form this carbocation. Once you form the carbocation, now this can rearrange as shown here. Due to 3-membered cyclic system, it can open up to give so this cyclobutanone derivative as the product. For example, if you take here acetone, it can undergo addition reaction, and once if you have this epoxide, which can, when you react with the acid, and it can convert into the cyclobutane derivative, which can be, if you have this ketone, which can be further converted into, for example, if you try to do oxidation, for example, hydrogen peroxide or MCBBA, you can try to oxidize into lactone. As a product. So, you can see here you can use sulfur based relyde for variety of synthetic applications. For in this case, for example, if you have simple dihalo compound, in this is more reactive comparing to that, because it is a good leaving group. Once if you have this diphenyl sulfide, you can undergo the reaction in the presence of silver tetrafluoroborate. You can have, once if you have this undergo substitution, you make the salt, and this when you react with the base, you make the ylide, which can now undergo addition reaction with the carbonyl compound. For example, in this case we have taken the acetone, you will be able to form this epoxide. Once you have the epoxide, when you react with the acid, it can open up to give this ketone. The ketone can be further oxidized by standard procedure, all of you know very well, and you can convert into lactone so as a product. Now, let us look at some rearrangements in this case of ylide, and if you remember, the earlier we have studied Sohn-Lett rearrangement. If you have, for example, this quaternary ammonium salt in the presence of base, you can, for example, sodium hydride, which can now undergo reaction. We have seen two plus sigmotropic rearrangement. For example, this can undergo reaction here, this can come here, this can go, and you will be able to form a product which involves 2, 3 sigmotropic rearrangement. And similarly, we have the sulfur ylide, and this also can undergo rearrangement. In this case, the one sigmotropic rearrangement is shown here, like Stevens rearrangement, if you try to remember, and quaternary ammonium salt, which can undergo 1 to sigmotropic rearrangement. Similarly, in this case, if you have the sulfur ylide, if you have the alkyl group, it can undergo rearrangement here. On the other hand, if you have the allyl one, and this can undergo 2, 3 sigmotropic rearrangement as shown here, you can go here, it can come, and you will be able to form this homoallyl thioether as a product. And now, let us take this example, and here this diallyl ether is shown here. When you thioether, when you react with ethyl bromide you will be able to get this salt. Once you form the salt, now when you react with the sodium hydride, you can deprotonate. For example, if you deprotonate, you get this halide. Once you have the halide, there are two possibilities there, as just we have seen. It can undergo 1:2 sigma-tropy rearrangement. It can shift here, and you will be able to, in this case, you will be able to get this compound. It can also undergo 2,3 sigma-tropy rearrangement, and in this case, it can undergo reaction here, and this will come here. Then you will be able to get this compound. Once if you have this compound, this you can do desulfurization using sodium liquid ammonia, you can get this alkene as a compound. So, if you have the allyl halide, it is prone to undergo 3,2 sigma-tropy rearrangement as shown here, and you will be able to get this alkene as the product. Now, let us look at some more related reactions. Here the rearrangement of this compound is shown here. You have this halide, as we can prepare this halide readily. Once you form this one, and as just we have seen, this also can undergo 2,3 sigma-tropy rearrangement as shown here, and you will be able to get this compound. Once if you have this one, this can convert into this aniline derivative. So, you can try to introduce thioether substituent and alba position through this rearrangement, and you can also, instead of nitrogen, you can also have oxygen. This also can undergo rearrangement, and you will be able to get this orthosubstituted phenol as the product, where you can introduce the thioether substituent through this rearrangement. Here the reaction of aniline with tetrahydrobutyl hypochlorite shown here, which can give this N-chloro compound, which when you react with dimethyl sulfide, you can make this salt. Once you make the salt, as just we have seen, you can try to react with the base, then you will be able to make, here they have used methoxide, you can make this halide. Once you make the halide, as just we have seen, it can undergo rearrangement, as shown here, and you will be able to get this compound, and you will be able to introduce this moiety. Once if you have this one, you can remove the thioether group by desulfurization by using nickel catalyzed hydrogenation. In this way, you will be able to introduce methyl group and the alpha position of aniline derivative. So, if you want to introduce alkyl group, and this one of the method, if you have the aniline, if you want to selectively introduce the methyl group ortho position, this one of the effective synthetic route, you can convert into this chloro compound, when then react with this dimethyl sulfide followed by deprotonation using base, you make the halide, which can undergo rearrangement as shown here. In this way, you will be able to make the thioether. Once we have this one, you can try to do the desulfurization by hydrogenation using nickel based system. It is well known in the literature. You can introduce the methyl group on the ortho position. Here another example shown, and similar to that, if you try to react with this chloro compound with this cyclic thioether, you can make this salt. Once you make the salt, as we have seen, you can deprotonate using methoxide, and you make this halide. Once you form the halide, as just we have seen, it can undergo rearrangement. You will be able to which can convert into so this 2 alkyl thioether derivative. Once we form this one, this way you can do the desulfurization using the hydrogenation using nickel catalyst. In this way you will be able to make 2 alkyl aniline. For example, if you use this cyclic thioether, you can introduce the N alkyl group, and this you can see selectively you can make this compound using this approach. The next example involves here this chloro compound reacts with this thioether, which has electron withdrawing keto group. As just we have seen, you can undergo substitution reaction, you can make the salt. Once you make the salt, now since you have the electron withdrawing group, you can use weak base like triethylamine, you can deprotonate, you make this ylide. Once you make the ylide, this can undergo reaction and you will be able to get this compound, and this can convert into this 2 alkyl aniline derivative. Once we have this one, you can do desulfurization. Before that, what they have done here, and it can undergo condensation to give this derivative, which can convert into indole, which with the thioether substituent you can try to remove the sulfur by desulfurization using hydrogenation in the presence of nickel catalyst. In this way you will be able to get the indole derivatives. As you can see here, it has wide applications in organic synthesis to selectively construct variety of heterocyclic scaffolds. Now let us look at the transformation of ketone to alpha beta unsaturated carbonyl compound, and in this case if you have the ketone and you can try to react with base, you can make this unolate. Once you form the unolate, which can undergo reaction with the disulfide, you can make this thioether derivative, which can undergo oxidation using MCBBA or hydrogen peroxide in the presence of catalyst like titanium 4. You can oxidize to sulfoxide. Once you have the sulfoxide, and which can readily undergo elimination, as you can see here, you will be able to get alpha beta unsaturated carbonyl compound. Here an example shown here. Let us take this cyclic ketone. So when you have the cyclic ketone, and this when you can try to react with the base, and you can make this unolate. So once you have this disulfide, then you will be able to have this which when you react with hydrogen peroxide in the presence of catalyst, for example titanium isopropoxide, you can convert into sulfoxide, so which can now undergo elimination as shown here, and you will be able to get alkene and thiophenol as the product. Now, let us look at the other type of reactions, the reverse polarity of carbonyl compound. So far we have seen two type of reaction. First one, the formation of halide and their addition reaction with the carbonyl compound. Then we have seen the, if you have the ketone, you can make alpha beta unsaturated carbonyl compound via elimination. If you have the sulfoxide which can undergo elimination to give the alpha beta unsaturated carbonyl compound. Now, let us look at the reversed polarity of carbonyl compound. For example, here the reaction of aldehyde with the Grignard reagent is shown here, and this can undergo addition reaction with the carbonyl group, and you will be able to get this magnesium alkoxide, this intermediate. Once if you do the workup, and you will be able to get the alcohol which undergoes 1:2 addition reaction. So, always when you have the nucleophile, the carbonyl group can prone to undergo addition reaction, you get the addition product. So, what we are going to look at, this is a very important, the sulfur chemistry, and if you have the aldehyde or ketone, you can try to reverse. If you look at the carbonyl compound, now this is electrophilic nature in the carbon, and the nucleophile can undergo addition reaction, and you will be able to get the addition product. Now, whatever we are going to look at it, the reverse of the polarity of this carbonyl group. Now, and if you convert this aldehyde into this dithioacetal, if you have this 1,3 propane dithiol, when you can the presence of acid, you can convert into dithioacetal. Once you form the acetal, now you can try to react with the base. You can deprotonate this proton, it's acidic. You can generate the anion. This anion can be stabilized by the d orbital of sulfur, now which can act as a nucleophile. You can carry out variety of reactions. For example, and if you have the aldehyde, if you want to make ketone, this is one of the efficient method. If you have the aldehyde, you can react with the dithiol, you can make this cyclic thioacetal. Once you form this one, now you can try to react with the base. If you have the alkyl halide which can undergo nucleophilic substitution, then hydrolysis you will be able to get the ketone as the product. Now, let us look at some example. Here the reaction of this dithioacetal is shown here. Since we have made from aldehyde, should be called as dithioacetal, and if you make from ketone, this is the dithioketal. And once if you have the dithioacetal, when you can try to react with the n-butyl lithium. So, when you, so it can act as a base, it can deprotonate, and you will be able to form this salt. Once you form the salt, and this salt, now if you have the alkyl bromide is shown here, it can undergo nucleophilic substitution by SN2 pathway, and you will be able to have this compound. Once if you have the compound, when you use this condition, hydrolysis can lead to the formation of ketone, and you get back your dithiol as a product. You can recover the dithiol. So, this is one of the effective route. If you have the aldehyde, if you want to make ketone, and you can use this approach, and you can make ketone. Now, let us look at another example. Now, this dithioacetal can be made from formaldehyde. If you have the you can make this one, you can deprotonate, and then you can make this salt which can undergo substitution here, and then you will be able to do monoalkylation here. Then you can deprotonate, and you can take another alkyl halide. It can be different or same, it can be different. Then you make this alkylation. Once you make this one, you can try to do hydrolysis, you can get the ketone as the product. For example, when you take this one, this dihalo substrate, when you react with the n-butyl lithium, you can deprotonate, and which can undergo substitution SN2 reaction, and you will be able to get this chloro derivative. Once you form this one, this can again undergo reaction, you can deprotonate it, you make the salt which can undergo intramolecular nucleophilic substitution. In this way, you will be able to make the cyclobutane derivative, which when you do the hydrolysis you will be able to make this cyclobutadiene as a compound. Otherwise, it will be very difficult to make this compound using this approach, and you can make this cyclic ketone and using this dihalo substrate. And here another example shown. Instead of that, if we have aldehyde, you can deprotonate, which can undergo addition reaction with the aldehyde. When you do the hydrolysis in this way, you will be able to make the alpha hydroxy ketone as the product. So, this one of the effective synthetic route. If you have the aldehyde, you can make ketone, or if you want to use react with another aldehyde, for example in this case, and you can also couple in this way, you will be able to make alpha hydroxy ketone as the product. Now, let us look at the Julia reaction, which is very important, the sulfur chemistry. And if you have the sulfone, and the sulfone has alpha hydrogen atom which is acidic enough, and which can, when you react this compound with lithium or magnesium, you will be able to make this anion, which once you form this one, which is stabilized by the sulfone, which can now undergo addition reaction with the aldehyde or ketone. You get this product. Once you form this one, when you react with acetic anhydride, you make the acetate, and once you form the substrate, when you react with sodium amalgam, it can lead to the elimination to give this alkene as a compound. So, if you have the sulfone which has alpha hydrogen atom, and you can try to readily react with the lithium or magnesium, you make this anion which can be stabilized by the sulfone, that can lead to addition to the aldehyde or ketone, and which can be further reacted with the acetic anhydride to get the acetate. Once we have the acetate, when you react with the sodium amalgam, now you can convert into alkene as the product. An example shown here, and in this case when you react with sodium amalgam and you can remove the sulfone, you get this anion here, and which can now as shown here convert into alkene. Usually you get the trans alkene, as you can see here. It can, in this case, it can undergo via SN2 pathway as shown here. I will be able to get trans alkene as the product. So far we have seen the fundamental transformations of the sulfur chemistry, and now let us look at the recent development in this chemistry. For example, if you have the sulfur halide, you can try to react with the ketone and you can get the epoxide, just we have seen. You can also add, in the place of epoxide, in the aldehyde ketone, you can also add with imine, you can get this acidity as a product. On the other hand, if you have the alpha beta unsaturated carbonyl compound, the halide that you generate from the sulfoxonium ion intermediate can undergo addition reaction with the double bond. In this way, you will be able to form activated cyclopropane as the product. So, these are the again fundamental and important transformation of the sulfur chemistry, and recently effort also has been made to construct these epoxides, acididines and cyclopropane in optically pure form using chiral catalyst. Now, let us look at one of the recent application of this chemistry. Here the reaction of this aldehyde with the diazo derivative shown here, the presence of proline and acetonitrile, what may happen here, which can undergo addition reaction here, then you will be able to get this addition product. Once you have here, now this halide what you have here, this undergoes reaction with this aldehyde addition reaction as we have seen here, then you will be able to get this intermediate. Now, proton exchange can lead to the formation of this can undergo now SN2 reaction, and in this way you will be able to form this heterocyclic compound. Here since they have used here L-proline as catalyst, which can lead to the formation of this heterocyclic compound with good enhanced selectivity. So far we have seen the organosulfur reagents, and first we have seen the formation of halides and their reactions with the carbonyl compounds. Then we have seen the transformation of ketone to alpha beta unsaturated carbonyl compound. If you have the thioether substituent at alpha position of the ketone, you can convert into the corresponding sulfoxide, that when you heat it, it can undergo elimination to give alpha beta unsaturated carbonyl compound. Then we have seen if we have aldehyde and you can try to reverse the polarity of the carbon, you can convert into dithioacetal or ketol, which can readily undergo reaction with base, and you can make the anion which can be stabilized by the d orbital of the sulfur, which can react with alkyl halide or carbonyl compound to give the addition or substitution product, which can be further manipulated to useful compounds. Then we have seen the Julia olefination. If you have the sulfone, if it has alpha CH bond, which can be easily converted into carbon ion using lithium or magnesium, which can be further reacted with the carbonyl compound, right, aldehyde and ketone to give the addition product, which can be further reacted with acetic anhydride to give the acetate. When you react this with sodium amalgam, the sulfone can be readily removed, where you generate the anion which can convert into olefin as the product. Then we have seen the recent development in the halide chemistry. Not only you can make you can add the halide to aldehyde and ketone, you can also react with imine, you can make acidine as a product, you can also add to alpha beta unsaturated carbonyl compound. In this way you will be able to make donor acceptor cyclopropane as the product. Now let us look at the silicon containing reagents. Here the Peterson olefination shown here, this is important reaction, the silicon chemistry. For example, here this methyl group is bonded with the trimethyl silyl group as well as the ester group, and when you have this substituent, you can try to readily react with a base like phenyllithium here shown here, and you can deprotonate, you make this anion. So this anion can be stabilized by this ester group as well as silyl group, and if it anion present the alpha carbon atom, the silyl group can stabilize this anion. And once if we have this one, this anion can readily undergo addition reaction with this carbonyl compound here, and you get the addition product. Once if we have this addition product, now this can undergo elimination here, you can form you will be able to get this alpha beta unsaturated carbonyl compound here. For example, shown here, if you have the cyclohexanone, you can make this conjugated ester using this approach. You can try to make this anion which can readily undergo addition reaction followed by elimination, you get this conjugated ester as the product. Now let us look at, so this is one of the approach, and the other approach is that you can also make carbon ion equivalent by as shown here. For example, if you have this trimethyl vinyl silane, and this you can try to react with organolithium as shown here, it can undergo addition reaction, you will be able to get this alkyl lithium where you have the trimethyl silyl substituent. And in another example, you have the trimethyl allyl silane where you can also try to react with base like alkyl lithium or N-beta lithium. You can try to react with the organolithium reagent, you can deprotonate, you can make this alkyl lithium where you have the silyl group as well as you have the vinyl substituent. The other example, if you have this substrate where you have this carbon is bonded with the trimethyl silane as well as chloro substituent, which can readily undergo reaction with the magnesium as we know, and you will be able to form this Grignard reagent where the trimethyl silane is bonded with methyl group, and these reagents also can be readily reacted with the carbonyl compound to give the addition product. Now let us look at some examples, and when is shown here, and this can readily undergo addition reaction with aldehyde or ketone, and you will be able to form this alcohol. And once you form this addition product, and this depends upon the reaction conditions. For example, if you use here potassium hydride, and you can make this alkoxide which can make bond with the silicon here, and you will be able to form and you will be able to get this alkene as the product. In this case you form the E alkene, and similarly on the other hand, if you have the Lewis acid instead of potassium hydride, it can make chelation with your alcohol, then you will be able to form this alkene. In this way you will be able to form the Z alkene as a product, and if you use the Lewis acid you get this. On the other hand, if you use potassium hydride as a base and you get the syn elimination, you will be able to get this E alkene as the product. Now let us look at here. Even you can try to transform trans alkene to cis alkene or reverse. For example, here the transformation of trans alkene to cis alkene shown here, E to Z alkene. This can be carried out if, for example, if you try to react with peroxide acid, you can convert into epoxide. For example, you try to react with metachlorobenzoic acid, in dichloromethane you can convert into epoxide. Once you form the epoxide, you can try to react with this trimethylsilyl anion, which can open up the epoxide via SN2 pathway. You have this one. Once you form this one, which can rotate to make oxygen silicon bond as shown here, and will make. So, this can now convert into the stereochemistry. You can convert into here E to Z alkene, and it has to rotate this bond. You make this intermediate. To form this intermediate, you have to rotate this bond. R prime comes this side. Once you form this, it can undergo elimination to give Z alkene as the product. Now let us look at the use of silicon reagent production of alcohols. This is also very important. This is also very important transformation in the silicon chemistry. If you have alcohol and which can be readily reacted with, for example, here with the trimethylsilyl chloride shown here, in the presence of base like triethylamine, you can make the silyl ether. Once you form the silyl ether, this is stable in basic conditions. However, acidic conditions, it can depends upon the silyl group. If we have the sterically hindered silyl group, we are going to look at it. They will be more stable under normal acidic conditions. And once the reaction finished, you can try to cleave this, deproduct the silyl group by hydrolysis. And if you see the reactivity of alcohols, primary alcohol shows greater reactivity comparing to secondary, and which shows greater reactivity compared to tertiary alcohol. Here an example shown here. Let us look at this one. You have one OH group, secondary OH group, which is cis to this R prime, and here you have another OH group which is trans to this R. So, among this, and when you treat this silyl reagent, which undergoes readily reaction with this one due to steric reason, the trans one undergoes, you can try to product this OH group. So, you can see here, so when you want to selectively product, for example, you have the tertiary and secondary alcohol. If you want to react only tertiary alcohol, what you need, you can product the secondary alcohol, you can carry out the reaction. After the reaction, you can try to deproduct the silyl group and you can get back your substrate. And similarly, for example, in this case, if you want to react this OH group, and what you can do, you can try to product this OH group using this silyl reagent, and after the reaction, you can deproduct this and you can get back your desired compound. Here an example shown. The use of tertiary butyl dimethyl silyl group is shown here, which is bulkier silyl reagent to product alcohol. And if you see in this reaction, always you can find the use of catalytic amount of imidazole in this reaction. This is because, and when you use alcohol and which is less nucleophilic comparing to imidazole, so when you have the catalytic amount of imidazole, which can undergo reaction with this tertiary butyl dimethyl silyl group via SN2 pathway, you will be able to get this adduct. Once you form this one, and which can now readily react with this your alcohol via another SN2 pathway, and now this is a good leaving group as shown here, and in this way you will be able to product alcohol using with this tertiary butyl dimethyl silyl group. You can make this silyl ether. Once if you make the silyl ether, which is stable under normal acidic conditions and basic conditions, and once the reaction finished, you can try to remove the silyl group by using the fluoride ion. If you have the tetrabutyl ammonium fluoride or any fluoride salt which can readily undergo reaction here, and you will be able to get the alkoxide, which can be, when you do the workup, you will be get the alcohol. This is because you make this the carbon, the silicon fluorine bond is very strong. Therefore, when you use the fluoride ion, which can readily undergo reaction with the silicon, and this in this way you will be able to convert, you can convert this silyl ether into alkoxide ion, once which can be when you do the acid workup, you get the alcohol as the product. So, now let us look at the other type of reaction. So far we have seen the silicon chemistry 3 type of reaction. First one was Peterson olefination. Then we have seen the use of silyl reagent for the production of alcohols. Then now let us look at the ipso substitution. For example, if you have the cation, the beta position, the compound where silicon is bonded here, for example, if you have a similar kind of structure, this carbon is bonded with the silyl group, and then you have here the beta carbon has a cation. So, this can be stabilized by the silyl group, and then for example, this vacant p orbital of this carbocation can be stabilized by this carbon silicon bond, and in this way, and you will be able to form, able to carry out ipso substitution. Now, let us look at this aromatic system which has the trimethyl silyl group, and when you react this with electrophile, for in this case the electrophile always undergoes reaction at the carbon where the silyl group is bonded. This is known as ipso substitution. This is because you have now this vacant orbital p orbital is perpendicular to the plane, and this carbon silicon bond can stabilize this carbocation, and you will be able to form this. Once you form this one, now this the silyl group can leave, and you will be able to get the benzene ring. And if you have this, you can see here the rate of the reaction 10 times greater comparing to the substrate that does not have the silyl group. It helps to activate the substrate. This is because, on the other hand, suppose the electrophile undergoes reaction here, so this the vacant orbital is perpendicular to the plane benzene ring. This is on the plane, so it cannot stabilize. Therefore, when the electrophile undergoes reaction where the carbon is bonded with the silyl group, and you will be able to have the tetrahedral structure which can, this carbon silicon bond can stabilize this p orbital. So, therefore, always the electrophile readily undergo reaction wherever the silicon is bonded, and in this way you will be able to oscillate the reaction to get the substituted compound. Now, let us look at some more example shown here. If you have the bromo compound, you can try to react with the lithium, and you can try to react with the trimethyl silyl chloride. You can try to introduce the silyl group. Once if you have this one here, the reaction of acetyl chloride in the presence of Lewis acid shown here, already we know that when you have the Lewis acid, this you will be able to form this acyl cation. Once we have this excess electrophile which readily undergoes reaction, in this case you can undergo reaction here, and you will be able to form once you form this one, now this can convert into as the product. And another example shown here, the preparation of vinyl silane is shown here. If you have the alkyne, you can try to react with trimethylsilyl hydride in the process of platinum catalyst, and then addition reaction can lead to the formation of this vinyl silane. And if you have the vinyl halide, and you can also try to react with magnesium, and you will be able to form this corresponding magnesium reagent. Once we have this one, you can try to react with the trimethylsilyl chloride, and you will be able to make this vinyl silane as the product. These are some of the methods how you can make alkynyl silanes. If you have the alkyne, you can do the addition reaction with this trimethylsilyl hydride in the platinum catalyst, or if you have the vinyl halide, you can also try to convert into the Grignard reagent, which can be further reacted with the trimethylsilyl chloride. You can get this vinyl silane as a product. Now let us look at the reactivity of vinyl silane. And once we form this one, now here the reaction with the acetyl chloride is shown here, the presence of aluminum chloride. As just we have seen in the aromatic system, here also it can undergo reaction, and you will be able to form this when you have this as just we have seen, and it can form undergo reaction, and you will be able to get this intermediate. Once you have this one, then you will be able to form ketone derivative. And here also you can look at here, the electrophile always undergoes reaction, the carbon where the silicon is bonded. And here another example shown, and this also you can see here in all this reaction, this configuration is retained. And here also in this case, similarly you can try to react with the iodine, then you will be able to get the vinyl iodide as a product. Now let us look at the stereochemistry, and if you have this vinyl silane, and when you react with the electrophile, we have seen several examples, acetyl chloride and iodines, and now this, as we have seen, this can undergo reaction, and you will be able to form this carbocation, the beta carbon. Once you have this carbocation, as just we have seen, it can be stabilized by this carbon silicon bond. Now this can undergo free rotation as shown here, and this free rotation, once you form this one, it can convert into alkene, and when you do the free rotation, and you can retain the configuration, you look at here, and the electrophile comes wherever the silicon is bonded, the same position, you can retain the configuration of this alkene. On the other hand, now let us look at here, if you want to invert, you have to react this vinyl silane with the bromine, and it can undergo addition reaction, then you will be able to get this intermediate. Now is a competition between another beer can undergo reaction via SN2 pathway, and you can react, you form the dibromo derivative. Alternatively, it can also the bond can rotate, and it can undergo elimination. In this reaction, the bromine, the reaction of Br minus is much faster comparing to the elimination reaction. Therefore, the addition of Br minus takes place. Once you have the anti-addition product, now it can rotate as we have seen, and it can rotate. You have this, once if you have this one, now this can undergo elimination as you have seen, and you will be able to get this vinyl bromide. You can see here this inverted configuration. Now you can see here, and this R prime come this side is trans to that, and this the bromine whatever substitution takes place, and is with inverted configuration. So if you want to make, you can see here, and see if you usually if you carry out the reaction with the electrophile, you retain the configuration. If you want to invert, what you can do, you can carry out as shown here. This way you will be able to get the substitution product with the inverted configuration. Now let us look at the preparation of allyl silanes and their reactions. If you have the allyl chloride and you can try to react with the magnesium and you can get the corresponding magnesium chloride, for example here you will be able to form this allyl magnesium bromide. Once if you have this one, you can try to react with trimethylsilyl chloride. As we have seen, in this way you will be able to make this allyl silane as the product. And for example here, and just we have seen the reaction with the vinyl silane. When you take the allyl silane, you can see here, and the reaction takes place here in this place. Now you get the carbocation in this position, the beta position, because this can be again stabilized by the silicon. Once we have this one, and it can convert into this alkene as a product. In addition to that, you can also carry out a reaction. For example here, if you have the allyl silane, which also can be reacted with for example aldehyde in the presence of Lewis acid, it can do the addition reaction. Asymmetric version of this reaction also has been considerably explored. Now let us look at some more example here, and you have here this carbon is bonded with trimethylsilane as well as Cl, which can, when you react with the base, you can deprotonate, you generate the anion which can be stabilized by the silicon as just we have seen, and you make this alkyl lithium. Once you form this one, which can undergo addition reaction with aldehyde or ketone as shown here. Once if you have the leaving group which can via SN2 pathway, and it can cyclize, in this way you will be able to make epoxide which has the silyl substituent. And this, once if you have this one, and this can be treated with acid and protonation, and followed by opening, you will be able to form this carbocation intermediate which can convert into this enol. This enol can be further transformed into ketone as a product. Therefore, if you have this, you can also try to react the carbonyl compound which can be converted into keto derivative. Here another example shown, the epoxide, whatever you generate here, the epoxide also can be reacted with, for example here with the Gilman reagent. You can try to open up and you will be able to get this product. In summary, so in this class we have seen the preparation and reaction of organosulfur and silicon reagents. In the case of organosulfur reagent, we have seen the preparation of sulfur ylides and their addition to carbonyl compounds. Then also we have seen the rearrangement. If we have the sulfur ylides which can undergo like Sohmlet rearrangement, they can undergo 2,3 sigmotropic rearrangement that can lead to variety of useful compounds. Then we have seen the reverse of the polarity of the carbonyl group. If you have the carbonyl group, if you react with 1,3-dithione diol, you can make the corresponding dithioacetal that can now be reacted with the base, and the base can stabilize the now deprotonate this proton. That anion can be stabilized by the d orbital of sulfur. Now we can react with variety of electrophile alkyl halide, or you can also react with carbonyl compounds and substitution reaction that can lead to variety of compounds. After the reaction, you can also remove the dithiol group via sodium using hydrolysis. Then we have seen the Julia olefination. If you have the sulfone, you can, if it has alba CH bond which can be converted into anion using lithium or magnesium, which can readily undergo addition reaction with the carbonyl compound. That alkoxide what you generate can be treated with acetic anhydride, you make the acetate. Once you form the acetate, now when you react with sodium amalgam, you can convert, you can remove the sulfone functional group. That sulfone now can convert into olefin, we have seen. Then we have seen the organosilicon reagent. We have seen the Peter olefination, which is very important reaction. Depends upon the reaction conditions, you can convert into carbon unequal silane which has alba hydrogen atom, which you can try to react with the base, deprotonate, which anion can be stabilized by the silicon, and which can readily undergo reaction with aldehyde ketone addition reaction to give the alcohol as the product, which in the presence of base you can convert into silyl ether and olefin as a product. in the presence of acid you can get the inverted configuration. Then also we have seen if you have the alkene, that also can be converted into, for example, if you have the E alkene, you can convert into Z alkene by epoxidation followed by opening by trimethylsilyl anion followed by reaction, elimination reaction to give this inverted configuration. Then we have seen the use of silicon reagent, the production of alcohol, which is very important transformation in synthetic chemistry. Your substrate has multiple functional groups. If you want to selectively protect the OH group, then you carry out the reaction of other functional group. You can protect the alcohol using silyl group. You can carry out the reaction. Once the reaction is over, you can also deproduct the silyl group using acid hydrolysis. Depends upon the nature of the protecting group. If we have, for example, we have seen one example, tertiary butyl dimethylsilyl group, which is commonly used, which is stable under normal acidic conditions. You can protect the alcohol group using imidazole as the catalyst. We have seen the explanation why imidazole is needed, because which can act as a nucleophile which can react with the tertiary butyl dimethylsilyl group. Once you form the adduct which can be reacted with alcohol, where via SN2 pathway you will be able to get this silyl derivative. Once if you have the silyl ether, once the reaction finished, you can try to react with fluoride ion. In this way you can deproduct the silyl group. Then we have seen some examples for allylation, how you can make this vinyl silane as well as allyl silane. They also have broad utilities. We have seen this one. The importance of the silicon chemistry is that if you have the alpha carbon has anion which also can be stabilized by the silicon. Similarly, if you have the beta carbon has carbocation which also can be stabilized by the carbon silicon bond. This is very important, the silicon chemistry. We also have seen several examples, the ipso substitution, and if you have the dimethylsilyl substituent where the electrophile can readily undergo reaction, and so the reaction can be accelerated. We have seen several examples, and as you can see here, this sulfur and silicon reagents have wide applications in synthetic chemistry. With this we conclude this lecture. Thank you very much.